going to look at some practice problems. So again, in our examples, we wanted this kind of a system, but it turned out we have an uncertainty that appears in this kind of system. So this kind of uncertainty actually has a name. It's called a multiplicative uncertainty. And so we saw that for this kind of uncertainty, with this uncertainty being plus or minus 0.5, we can apply a closed loop system, and this is our closed loop. So we have 100 over 1 plus delta over 1 plus 100, 1 plus delta. So, and we can convert it this way. How did we get this? Well, if I take this inequality and this fraction and add in the numerator 1 minus 1, right? So we're actually not adding 0. We're adding 0. So if I add 1 to this, then I have exactly the denominator. And so that's this term, and then minus 1 over this. And so that's how we get this. So this is an uncertainty term now. So we've transformed our uncertainty into uncertainty like this, into an uncertainty like this. That uncertainty delta is a number. That's what we're going to call that delta tilde. Delta tilde now as a number is between 0.00662 and 0.02 basically. And so if we look at this quantity now, we have something between 0.98 and 0.99. So we're within 2% of having exactly 1. So even though we had an inaccurate, and so I call this a power amp because this is the kind of thing that we have. So for example, with an old transistor amplifier, we have these kinds of things where you have the transistors were notoriously uncertain in many ways. But when you apply feedback, then you can actually get a fairly good amplification. So using feedback was one of the early applications of for uncertainty like that. Here we have an uncertainty entering in the same place as our control signal. So they basically have the same authority as one another. That is, this one can control my system just as much as this one. By applying a closed loop and actually this gain, we actually have upped the authority of our system. Okay? And so by upping that authority, our transfer function now is given by this instead of this. And when k is equal to 50, this is what we get, a signal-to-noise ratio of 32 dB versus a signal-to-noise ratio of 0 dB. Okay, so we have that kind of result. So W here has a lot of authority. W here has very little authority. Okay, and the feedback helped because of the high gain. It basically gave more authority to this signal, which is getting multiplied by that, than this signal has. In terms of structured uncertainty, suppose that the exact values of our masses and springs and all those things, suppose that those have uncertainty associated with them. Well, here is a model for, so if we go through and actually obtain a state model for our system, this is what we get. And now I'm going to assume that M1 is uncertain. And notice that wherever we see M1, we actually see M1, 1 over M1, right? So I'm going to assume that M1 is uncertain and that M1 is in this set, okay, between alpha plus or minus delta, basically, is what we have. Alpha plus or minus delta. Okay, so delta is an uncertainty, and alpha then is the nominal value of 1 over M1. So given this system then, I can define the nominal value of A. So notice that it just involves alpha, which is the nominal value of M1 over M1. Okay, and notice that the M2 is not affected here. So, but alpha appears here and it appears here. Okay. The H matrix. So notice that each of these terms involves the uncertainty, right? So wherever we see alpha, we also actually have a delta there. So each of these terms has uncertainty. That's why the G is this way, because that actually should be a 1. Yeah, that should actually be a 1. And then, yeah. And then this vector is actually all of this. So it's times A, but here it's also times delta. And so we have that. And so our uncertainty then can be, A then can be written as this plus G times delta H. So if I multiply G times delta times H, I get the uncertainty appearing in this row that is in the M1s. Okay. And similarly, in my B matrix, I'm going to have, so this is my B naught, which is 1 over, the alpha is the nominal value of 1 over M1. And then I'm going to have G delta C. So C is just the quantity 1. And so this is what we have. So, so this is our uncertain system. This is our uncertain system. And we've shown how we can take a problem and set up the matrices so that we can get it in this form, okay, with the matching conditions. So now if we actually work with numbers, suppose that 1 over M1 is between 1 and 3, and again, this is in some units, maybe tons, and alpha is 2, okay, so the nominal value is 2, alpha is 2, and so, and let's suppose 1 over M2 is 1/5, and we have these values for K and B. It turns out we can go through and show that if we have this matrix, okay, and this matrix Y, that we can obtain this state feedback gain K that stabilizes our system. So this basically makes A plus BK. Remember, A and B have our uncertainty in them. So this makes it uncertain. This makes it stable for all uncertainties, and it satisfies this linear matrix inequality. Okay, so somehow or other, I found a P and a Y that satisfies this linear matrix inequality. Wow, how did that happen? How to find those guys? Well, you know the drill.